there are situations where we want to calculate an integral, and we actually have a pole on the real line. And if we have a pole on the real line, then our methods just don't work in the same way. So suppose we want to calculate the integral from minus infinity to infinity, f of x dx, but f has a pole on the real line. Yeah, but it turns out if we have a simple pole, or indeed any finite number of simple poles, then we can actually do this. And we have to think what we mean by this integral in that case. We have to think about what we mean. So just think about f as a real valued function. If we have a simple pole, then it's going to blow up in some way, right? It's going to blow up. So the simplest example is 1 over x. So 1 over x blows up like this. It blows up and blows down. Yeah? Yeah? So if we integrate 1 over x from 0 to 1, as you guys know, this is infinite. This doesn't converge. Yeah? But if we take a particular kind of integral where we're going to integrate from delta to 1 and also from minus delta to 1, and we add those up, and then we take the limit as delta goes to 0, that thing actually will converge, because these things that are blowing up will cancel each other out. Yeah? So let me write that down. So the limit as delta goes to 0 of the integral of minus 1 to minus delta. I'm going to put union here just to save writing delta goes to 1 of 1 over x does converge and is actually equal to 0. So this thing does make sense if we do this in a particular way. And this is kind of an analog of Cauchy principal value when we took to infinity simultaneously from the left and the right. Yeah? So in calc, we talk about improper integrals of type 2, where we take the limit towards this singularity and just from one side, and if this limit exists, we say therefore we have a meaningful integral. But we can instead do something like this, where we insist that we simply exclude a little ball around the singularity or a little interval around the singularity. Yeah, because if we exclude a little interval around the singularity, then it is a meaningful integral. And if, as we exclude this little interval, then we can let the size of the interval go down to 0, and we still get a meaningful answer, then we say, okay, that's what we're defining the answer to be. So this is like taking the interval minus 1 to 1 and simply taking away the interval minus delta to delta, 1 over x dx. And this thing turns out to make sense. And the minus 1 to 1 could have been actually anything, right? It's just convenience. The point is that if we just take away a little neighborhood around the singularity and pass the limit, it's still going to have a convergent integral. Huh? So this is also called Cauchy principal value, but it's in a somewhat different sense. And that's how we're going to deal with, so I'll call this Cauchy principal value. And this is actually really useful because it turns out there are many very important integrals we need to calculate where we have to think of it in this way. And that's how we're going to consider these guys. So if f is some function that has a pole on the real line, then we are going to simply take out a little interval around this particular point, get some answer, and then if, as we let delta go down to 0, we get a consistent answer, then that's how we define this integral to be. And that's going to be fine. That's going to be okay for us. Okay? So that's how this thing will make sense if we have a pole on the real line. Cool. So, how are we going to do this? So, using complex analysis. We will consider, or we want to consider, the integral from minus r to r, f of x, dx, or I should, now that I'm being more precise, now I'm talking about principal value, I'm going to write PV, principal value. So I'm not specifying where the singularity is yet, but I'm just saying that this is not the normal notion of an integral. This is where we cut out the singularity and then take the limit. So we want to consider this thing as part of a contour. Yeah. So we've been making the selections of a rectangle or a semicircle, right, where we went minus r to r, like this. If we did a semicircle, so we can do a semicircle whenever the degree of the rational function is -2. The degree on the bottom is at least degree on the top +2. Then a semicircle works. So if we did a semicircle, then what we would do is we'd have some issue because there's a pole right here. So we can't directly apply the residue theorem because the residue theorem holds true when we can have the curve in the part where it's actually holomorphic and makes sense, right? We have to put all of our theorems together. We're not allowed to take the curve through the singularity where it's not holomorphic. You know? So we can't directly go through this thing and have any meaning to it. So what we're going to do is we're going to just take a little bump around it like this. Just take a little bump around it. And that thing will miss our singularity. That thing will miss our singularity. And presumably there will be singularities in this upper half of the semicircle. So then we can actually apply the residue theorem to this contour. Yeah? Yeah? And what will that give us? That will give us the complex integral of around this particular contour. So if this thing is, say, delta, then this will depend on delta. Yeah, and ultimately we're going to take delta go down to 0. But if we do this, let me say that a better way. So let me start that again. So if we take this contour integral, then doesn't matter how small a neighborhood we take, then sure enough, we can calculate what this thing is. We can calculate what this thing is. It's just the residue theorem. We just calculate the residues all here, right, and add them all together. That's no problem. We're going to let things go to infinity and to 0 in order for us to get something like the thing that we're actually looking for. Yeah, the thing we're actually looking for. Yeah, and previously we learned that if we let this r go off to infinity, then the integral around this complex part right here, sorry, the integral around this semicircle part just vanishes and we don't care about it. Yeah, and that was the same thing we did when we had a rectangle. The sides just are not important. Now in this case, we can't do that. It's not so simple. We can't just say, all right, we've missed out this. Let's just ignore this semicircle. It's small. Let's pretend it's not there, because that's not true. The integral of the function on this semicircle doesn't vanish as we let the radius of this semicircle go down to 0. It just doesn't vanish. And we're going to see that. Yeah? So we'll have the answer to what this contour integral will be, and it will be the integral from here to here, then the integral around this semicircle part, and then the integral from here to here. And again, this semicircle part doesn't vanish. Okay? So let me write that down. So we'll find so I'm taking the simpler case now when I just have a semicircle for the top. Again, that holds true whenever we have the degree of the rational function is -2. This also works when the degree is -1, and then we have to take a rectangle, but I don't want to have too many indices floating around, so I'm taking the simpler case. All right, so we will take this thing, the integral around delta r of our function, f of z. dz. And for sure, this is something that we calculate. This is the sum of the residues. Let me just put it in here. So that's the sum over I of 2 pi I times the residues, or 2 pi I times the residues at zi of f. This is something we can calculate. And as r goes to infinity, the semicircle part, which is harder for me to express in this way. So the semicircle, we will denote the semicircle as S of R. So this is the semicircle. Semicircle is S of R. As R tends to infinity, it will be the case that the limit as... So that's repeating itself. All right. That's stupid. Let me do this better. As R tends to infinity, the integral around the semicircle of f of z dz will go to 0, so we don't have to care about that part. No? But let's call this little bump thing here, let's call it, well, let's give this singularity a name. Let's call this Z0, and then let's call the bump part here C plus Z0. So that's the upper semicircle of radius, not R, delta, around Z0. No? But this thing, put it over here, the limit as delta goes to 0 of the integral around this guy is not equal to 0. We can't just ignore it. We can't just ignore it. Yeah? So this would be completely lost. We wouldn't have any success with this. We wouldn't be able to do anything unless it turns out that we can actually calculate explicitly what this is. Yeah? But that is the case. We can explicitly calculate what this is. Yeah? Yeah. So it turns out, and I'll show you in a second, this thing, the limit as r tends to 0, c plus delta of z0, f of z dz, will turn out to be just pi I times the residue of f at z0. Okay, so it is like contributing half of a pole. It's like contributing half of a pole. Yeah? So this thing will actually be this quantity over here. So that when we take r to infinity, we'll have the integral along the real line from minus infinity up to here. And then we'll have this part, which we know what it is, and then we'll have the integral from here to infinity. So if I write that in the language of maths, so taking to infinity, we will have the integral from minus infinity up to z0 minus delta. So z0 is on the real line, so this is a meaningful thing. Yeah? Of our function, f of x dx, plus this guy right here, because we can't ignore it because it's actually there, and then the integral from the real part from here onwards. Okay, and all of that stuff will be equal to the Cauchy principal value. Sorry, will be equal to the residue formula answer that we have here. The sum over these residues over ZIF, like this. Okay. So that is just because we know that the upper semicircle will vanish. Yeah. And the game would be lost. The game would be lost unless this thing that has to be included in our expression was calculatable. But it is calculatable, as we'll see, and it's not particularly hard. So this is the integral from this to infinity, like this. So if this thing I just claimed is actually true, then we're okay, because this guy, which is messing things up for us, we can take the limit as delta goes to 0 and know exactly what it is. Yeah? So then we can just put it onto the other side. We can just put it onto the other side. Actually, I should do this right. So look at this carefully. If we go around like this, then this part here is going around in a clockwise way. It's going around in a clockwise way. Yeah? And we are going to think of this as part of the semicircle. So semicircle is part of the circle, which we go around in an anti-clockwise way. So that's how I'm going to do it in all the calculations. I'm going to do it in an anti-clockwise way. So this won't be, so implicit in this, if the orientation is anti-clockwise, this won't be like this, it'll be minus this. It'll be minus this. If I specify that I'm going anti-clockwise around the semicircle, which I will do because that's what we do all the time with circles or with anything, any closed curve. Yeah? So it actually minus this. Yeah? Cool. So then we can put this on the other side, and on the other side we're just going to add half of a residue. We're just going to add half of a residue. Yeah? And then as delta goes to 0, then these remaining parts right here this gives us exactly the definition of the Cauchy principal value that we're looking for. Yeah? So we'll be able to calculate the Cauchy principal value of this thing via this procedure, assuming this is correct, and we can actually calculate this. Is everybody happy? Okay, so what I really want you to do is not memorize this. I want you to be able to get this right formula from drawing this picture, from going, okay, I go around like this, from knowing that you can't just ignore this semicircle part, and the calculation I'm about to do will show you that. Yeah? Then looking at this and going, okay, well, if I go round anti-clockwise, then this semicircle part I'm going round clockwise. Yeah? So if I try and explicitly calculate it going anti-clockwise, I'm going to have minus this expression. Yeah? And therefore, the Cauchy principal value will be all the residues plus half of the residue, because I can explicitly calculate this when we take the orientation to be anti-clockwise, to be exactly half of the residue there. Yeah? So an easy thing to do is to just try and memorize the formula. And I'll be very upset if you get the formula wrong, because that will be my conclusion that you've memorized it, and I don't want you to memorize stuff. Memorization, again, is forbidden. Switch off your ability to memorize stuff. Yeah? Draw this picture for yourself. Just look at it, and then you'll see that this is natural. This thing is the only way it can possibly be. Yeah? Cool. All right, so I owe you this thing. And once we have this thing, then we have a formula we can explicitly use, and then we'll do an example. So let's, yeah, there's no space. Let's just erase the board and show you the thing I claimed. Proof of claim. Suppose F has a simple pole at Z0. Then the limit as delta goes to 0 of the integral around the upper semicircle oriented anti-clockwise of f of z dz is equal to the residue of f at z0 times I times pi, like this, instead of I times 2 pi as we normally would have. Okay. All right, let's see why. So proof of claim. Probably I should put claim first and then I should have put proof. Let me put claim. And now let me put proof. Okay, so since we have a simple pole, then we know it can be written of the form like this. F of z is equal to a to the minus 1 z, let me put it underneath maybe, z minus z0 to the power 1, and then just some holomorphic function g of z, where g is holomorphic. Let me do this better. So with this, for all z inside a small neighborhood, say B0, Z0, comma, where G is just a holomorphic function. It's just a holomorphic function defined in this neighborhood. Yeah, this is what we know. This is just from the definition of a simple pole, just using Taylor expansion. Right? Cool. So then we can try and explicitly calculate this integral like this. Yeah? Okay, let's do it. So take a parameterization. Equals z0 plus delta e to the it, like this. And then put it into this thing. So then the integral of c delta plus z0 f of z0 dz is equal to the integral from 0 to pi. It's half of the semicircle, right? Let me draw a picture. So we're going like this to this. Start here. Right, so this is z0 plus delta, and we end up over here. Yeah, so this guy is just integrated from 0 to pi. Yeah, so then we're going to have f of z of t, and then z prime of t. Let's put it here. Z prime of t is equal to delta I e to the it. So delta I e to the it. Like this, dt. And let's put in what our explicit form of f is. So this is the integral from 0 to pi, like this. I think I want to pull out the I and the delta. Why not? So then if we explicitly put this thing in, then we are going to have a to the minus 1. And this is our parameterization, right? So when we take z of t and subtract z0, then we're just going to have delta e to the it on the bottom here. Yeah. And then we're just going to have, and this guy I'm not going to write out in terms of explicit form because I don't need it. Just put this as z of t. And that is this stuff. And all of this stuff, therefore, is multiplied by e to the it dt. Everybody happy? Yeah? Okay, so let's break that up. Let's pass this e to the it through, it's going to cancel with this, and this delta is also going to cancel with this. So we're going to have an I integral 0 to pi, and just a to the minus 1, and that is all we're going to have, right? So this cancels with this cancels with this, so that's all we have for this part. And then the second part, we're going to have plus I integral 0 to pi. And what we have g of z of t e to the it dt. That's this, and then what is left? Yeah? Cool. All right, so this part is fine. We are happy with this. Yeah, this part is fine. So that is just I pi a to the minus 1. And then if we look at this part, well, g is a holomorphic function, right? G is a holomorphic function. And z of t is getting closer and closer just to z0, where g is nicely holomorphic. Yeah? This thing is just a complex number of size 1, so we can take the absolute value through this thing and see that it's actually a small expression. So let me write that formally. Let's do it this way. So if we take the absolute value of this thing, c plus delta of z0 f of z dz minus this term here, I a to the minus 1 times pi, then what we have left is delta. Let's take the absolute value through this thing, integral 0 to pi, the absolute value of g of z of t dt, like this. Yeah? And again, g is nicely bounded, right? Because we are close to this singularity, where g hasn't got a singularity here. G is just holomorphic. Yeah? So by continuity, this thing is less than twice the absolute value of g of z0, so long as we let this delta be small enough. Do you see what I mean? Or shall I add the details? Yeah? So look. So for small enough r, then g of z minus g of z0 is less than absolute value of g of z0 over 2. Yeah. Maybe it's actually 0 itself, so plus any alpha, which is small. So let alpha be 0. I think it's not actually 0 because of a construction. Anyway, so this thing is less than this thing, right? So if we are integrating on this little ball like this, then the z are indeed sufficiently close so we can uniformly bound it. Yeah? So then this thing is less than delta times pi, the supremum of g. Actually, I could just do it this way, just the supremum of g on this semicircle like this. C plus delta of z0. This thing, as we've just seen, is bounded, so then this thing goes to 0 as delta goes to 0. Yeah? So, that shows exactly our claim that the limit of this thing is equal to this thing, which is exactly what we said. A to the minus 1 is the residue. Cool. All right, so with this, we're in a position to calculate actual integrals f from minus infinity to infinity, where we have poles on the real line. In fact, we can have more than one pole. We can have any finite number of poles, and this thing would still work out fine. Yeah?